CalBridge program. And so our second speaker here is Katy Rodriguez Wimberly. Before I introduce her, we just wanted to acknowledge the fact that there is a nationwide, or maybe beyond that, scholar strike that has been called for today, which is intended to bring attention to issues of racism and inequality and police violence. And we felt after discussing this was an activity that is helping these goals of bringing awareness and trying to bring more equality and diversity into our scientific community. And so in that light, we are continuing with our seminar here today. So let me introduce our speaker. So Katy Rodriguez Wimberly started at Mount San Antonio College, a community college, and then went to Cal State Long Beach, where she did a bachelor's degree in physics and was a CalBridge scholar there, an important connection, obviously, for what we're doing here. And then she started on a master's program there and then transferred to do a PhD program at UC Irvine, where she currently is working on a PhD in physics. And she's also an NSF graduate research fellow there, which is a great accomplishment. She is on the Astronomical Society of the Pacific's board of directors, and has been leading peer mentoring programs that she created at UC Irvine and in CalBridge. We're going to hear about her research here today, which involves galaxy evolution using optical telescopes and cosmological simulations. So we're very pleased to have Katy here as our second speaker, and turn the floor over to you.
Awesome, thank you, David. Okay, let me share screen and play. Okay, can everyone see my screen? Share screen is good? Okay, looks like it, awesome. So yes, thank you all for coming today. To all the organizers, a special thank you for hosting me. I'm really excited to talk to y'all today about my science. And then towards the end, I'm going to talk a little bit about how kind of my STEM journey, how CalBridge has really very positively affected my life and career, and then a little bit about the DEI work that I do. So for my science, as David mentioned, I study galaxy evolution, and I focus on the very smallest scales. So today I want to talk about star formation quenching in particular. So this is how and when star formation ends in a galaxy, or new star formation ends in a galaxy, and then how we can use these smallest scales to kind of look and refine the mass of the Milky Way's dark matter halo. So these smallest scales that I'm talking about are called ultra-faint dwarf galaxies. They are these very, very tiny little galaxies, the tiniest we've ever seen. And they have some similarities amongst the population that we have been able to observe. They, aside from being all tiny, all ultra-faint, as the name suggests, they are all ancient, so they have very old stars in them. And the other really kind of standout thing about them is we've only been able to see these around the Milky Way. We've seen a couple within the dark matter halo of Andromeda, and a few, one or two kind of in between the Milky Way and Andromeda, but the vast majority that we've seen ever are within the Milky Way's dark matter halo. And I'll get to kind of what those distinctions are in a minute. But these kind of key facts, that they're tiny, they're ancient, and we can study them fairly well since they're nearby, have kind of brought up this question of, is it possible that these are the very first galaxies that ever formed? Are they fossils of the first galaxies ever formed? So to put this in a bigger context, Here we have a graphic of the early ages of the universe. So on the left, we're starting out with the Big Bang. The universe goes into these cosmic dark ages, and then the first stars start to form, and the first galaxies start to form. And then we enter the reionization epoch. And it's theorized that some of those first galaxies that formed, probably the tiniest ones, actually stopped forming any new stars during the reionization epoch. So these would be tiny and ancient galaxies today. And that leads us to think that our ultrafaints may be these fossils of the first galaxies ever formed. And when we look at our ultrafaints in certain ways, there's evidence to support this fossil theory. So here we have star formation histories of 6 of our ultrafaints. And just to describe the plots real quick, the vertical axis is just a cumulative culmination of the star formation history. So what fraction of the stars in that galaxy were formed across what time, where the horizontal axis is time. You have redshift on the top, which is Z, or on the bottom in billions of years. And as you can tell, across all 6, they've pretty much stopped forming all their stars by about 10.5 billion years ago. So we can really easily say that they're all universally ancient stellar populations. But when we look at these 6 galaxies in a different way, it's kind of evidence against them being fossils of the first galaxies. So on our left-hand plot, these are both phase space diagrams, meaning on the horizontal, we have a distance, so just line of sight distance from the center of the Milky Way out to the galaxy. And then on the vertical axis, we have velocity. So both of these are like line of sight velocity or radial velocity from the center of the galaxy to the Milky Way to the center of the other, to the satellite galaxy. So here are on the left-hand side, the observations of our 6 galaxies, and you can see they're all kind of in towards the center half of the Milky Way's dark matter halo, which we think is about 300 kiloparsecs in radius. And then if you compare that to simulations of a Milky Way-like systems, as you see on the right-hand side, all of those kind of center blue dots, all of those subhalos, dark matter halos that house galaxies like the ultra-faint dwarf galaxies, they fell in a long time ago. So they've been around the Milky Way for, as you can see, like 9-10 billion years, which means that the Milky Way may have had time to quench the star formation in our ultrafaints, or it's the environment of the Milky Way's dark matter halo that may have shut off new star formation in these galaxies. So I kind of have 2 situations here. We have evidence showing that these may be fossils of the very first galaxies ever formed. And we also have evidence that the Milky Way may be the main kind of culprit in shutting down star formation in these galaxies. So to kind of pick apart which one of these are, since it's very hard to observe the beginning of the universe, we can't really look and see what happened back in time. But I can continue to compare observations and simulations. And I can at least say, if I have 2 options, if I say it's not one option, it's not environmental quenching, then I can take that out of the running. So here we go. So this is exactly what I did in my first project. Here is, before I started my work, this is what we knew about how long it took galaxies to stop forming new stars once they became a satellite of the Milky Way, or once they fell into the Milky Way's dark matter halo. And as you can see on the horizontal axis here, we have stellar mass. So this is just in units of the mass of the sun, how massive or how big a galaxy is. And then on the vertical axis, you have quenching timescale. So how long did a satellite take to stop forming any new stars once it fell into the Milky Way's dark matter halo? And so you can see we have a lot of information here, but they're all on these much more massive scales. On this left-hand side at like 10 to the 4, 10 to the 5, we don't know anything. And that's the mass range of our ultrafaints. So what I did was wanted to compare observations to simulation. But let me take a step back and kind of give you this big picture of what environmental quenching is, and satellite galaxies and field galaxies and all these terms that I've been using for the past few minutes. So we believe that every galaxy lives within a dark matter halo. And so you can have a large galaxy in its own halo and a smaller galaxy in its own halo. And the smaller galaxy, right now, we would call it a field galaxy. It's not nested within some bigger system of dark matter halos. And so as these, we can also say that this field galaxy is currently forming new stars. So baby stars are popping up all the time in this little galaxy. And as everything's moving about space, our field galaxy may fall into or be pulled into the dark matter halo of a larger galaxy. So now our smaller galaxy is kind of nested within multiple dark matter halos. So this is when we call the smaller galaxy a satellite galaxy. Just means it's within the gravitational pull of the larger galaxy's dark matter halo. This larger galaxy now becomes a host galaxy. And so again, as we're moving about space and time, the satellite galaxy, which was once forming stars, may, through various mechanisms, stop forming new stars. And so now this is a quenched satellite galaxy. And this time scale, all of these mechanisms that can cause new star formation to end in a satellite galaxy have different time scales associated with them. And this time scale is, if I start a clock right when a galaxy falls into a larger dark matter halo, right when it becomes a satellite, I start my clock, and then I stop it when it stops forming new galaxies. So that time it takes to stop forming new galaxies as a satellite is my quenching time scale. And if I have the age of stars from observation and a simulated infall time from cosmological simulations, then I can easily get this quenching timescale and then start to look at the mechanisms that actually physically cause the stars to stop forming. And so this is exactly what I did with our little population of ultra-faint dwarfs. I used the Elvis simulation, which is a simulation of 48 Milky Way-like hosts. So there's 12 like boxes that have 2 hosts in them. So a Milky Way-like host and an Andromeda-like host, and then 24 that are just strictly like the Milky Way. And in this simulation, it's just dark matter only. And this was created by Shea Garrison Kimmel at UCI in 2013. So what I did with this is I went in and I pulled out the subhalos, or the dark matter halos that would host a satellite galaxy. I pulled out the ones that I would think hosts the ultra-faint dwarf galaxies. And then I did another little bit of calculation beforehand, because in simulations we've noticed that there's some that baryons, or like visible matter, can actually have some disruption on the dark matter subhalos that we didn't think was possible beforehand. So what this is basically some of our tiny, tiny dark matter halos, as they get close to the greater gravitational potential that's in the center of a host dark matter halo, they can start to get destroyed. And this kind of effect isn't strong enough in the Elvis simulations as we think is now real. And so what I did was I went in and just kind of using various prescriptions, I was able to randomly destroy some of the subhalos so that the counts of, tiny dark matter halos in our simulation are closer to what we see in the actual universe. So I actually cut out about 25% of my original population to be a little more accurate. And so now I have, across these 48 host dark matter halos, I had a population of small halos or subhalos that would house our ultra-faint dwarfs. And then I played this game. So my game was, I went in and I randomly grabbed 6 subhalos to simulate the 6 ultra-faint dwarf galaxy star formation histories that I showed earlier. So I randomly grabbed 6 and I played this game where I do all 6 of this random selection fall in or become satellites by some given redshift. And what's the probability of that if I select 6 10,000 times? And so as you can see by the teal line here and the purple line as well, but primarily the teal line, that I have a very, very low probability that all 6 of those subhalos had fallen in by some high given redshift that had fallen in far back in time. So to kind of explain this plot a little bit more, the vertical line or the vertical axis here is the probability that the environment of the Milky Way's dark matter halo had time to stop new stars from forming in our ultrafaints by the time, you know, they had fallen in until today. So did they have a long enough quenching timescale to actually quench new stars from forming? And then the vertical or the horizontal axis is redshift or time. Oh, I went the wrong way. Sorry. Okay. And so again, just to reiterate this point, randomly selecting groups of 6 10,000 times, I have a very, very low probability, a vanishingly small chance that the Milky Way's dark matter halo's environment had time to stop all of the stars from, any new stars from forming in our 6 ultrafaints, so that the stars in it would be all older than 10 billion years old. So I'm saying here that there's no chance the Milky Way could have created or could have left these ultrafaints with all ancient stars in them. Now, one thing, like, that's great, and that's the first point of evidence towards yes or no, the environment did not quench them, so it is probable that the reionization suppressed their new stars from forming, which would make them fossils. But there are not just 6 ultra-faint dwarf galaxies. And there's not even just 6 that have those star formation histories. I can add another 4 that have more star formation histories that were observed and calculated by Dan Weiss in 2014 and 2015. And then with the Dark Energy Sky Survey, there's a whole slew of other galaxies, ultra-faint dwarfs, all of these, that have some kind of metallicity information, observations of what the stars in these galaxies are made of. And that gives us some hint as to how old these galaxies are. And all of these on this phase space plot are universally ancient, and they're all ultrafaints. And now, since I've made this plot last year, there is even more confirmed ultrafaints and even better metallicity information, which continue to point to their very, very old stellar populations. So, okay, if I want to be more robust and not just say that I randomly select 6, what if I randomly select 10 or 20 to better match our actual ultra-faint population? Well, as you can see, as I go from selecting 6 to 10 to 20, I'm just getting less and less chance that the environment could have quenched the star formation, could have quenched the star formation in these satellites. So now I can very confidently say that there is less than 0.1% chance that the ultrafaints had their star formation suppressed or quenched or ended by the Milky Way, which then kind of leads to the fact that they probably are fossils of the very first galaxies ever formed. And again, just to be a little more robust, I wanted to look at the possibility that maybe not all 6 or 10 or 20 are quenched. What if only 75%? We kind of loosen the constraint a little bit and say that only 75% of the sample are quenched. And again, it's a little bit higher probability, but still very, very low. And the one other thing I looked into is, as I mentioned at the very beginning, there was a few ultrafaints that we have seen that are not really within the Milky Way or Andromeda's dark matter halo. One of these is Eridanus 2. It's literally like maybe 70 kiloparsecs outside of where we think the dark matter, the Milky Way's dark matter halo gravitational pull would really have an effect on it. So this is a field galaxy, Eridanus 2. So I said, okay, with this kind of oddball, what if I played the same game, but I selected only subhalos that would house an Airy 2-like galaxy? Well, if I have just a sample of one, and they all live right outside of the dark matter halo, this kind of ups the chance. And now the probability is slightly less than 10% that the environment of the Milky Way, like Airy 2, had fallen into the Milky Way for some time, had its star formation ended, and then left the Milky Way. That's a possibility, but it's less than 10% possibility. And because a sample of 6 is more robust than a sample of 1, kind of oddball out there, we went with saying that I can add to this big picture of satellite quenching by saying at the smallest scales, it is not the environment that is stopping star formation from continuing. And so it probably is reionization. So these ultrafaints probably are fossils of the very first galaxies ever formed, which was, I don't know, I was really excited that that was my first author paper ever in grad school. So now that this was all wrapped up in a pretty little package, pretty as it can be, I wanted to take our ultrafaints and kind of look at them or see what they could tell us about the universe in a different way. So in 2018, the Gaia Space Telescope put out its second data release. So Gaia is this amazing mission where they want to get proper motions of over 1 billion galaxies in and around, or not galaxies, they want to get proper motions of 1 billion stars in and around the Milky Way galaxy. Yes, the Milky Way galaxy. So a proper motion is the actual tiny motion of a star in space. You know, if you go out and look at Polaris, every night you go out and you look at Polaris, you're going to see it move slightly. Well, not Polaris, but you'll see other stars move ever so slightly every night. And that is indicative of our movement in our orbit. But if you have amazing precision, you can actually see the star move in its orbit and not just us moving in ours. And so the Gaia Space Telescope, it has a precision of hundreds of micro arc seconds per year. So to give this a little bit of perspective, 10 micro arc seconds is essentially seeing a quarter on the moon from Earth. So if you have 10 quarters on the moon, if you could see a star moving just that little tiny bit of distance, that's the kind of precision that Gaia has when it's getting these proper motions. And so it's collecting all of these proper motions of 1 billion stars around us. And what we can do with that is kind of put together the proper motion of an entire galaxy. So all of the stars observed in one galaxy that have these proper motions, you can calculate it out and get the proper motion of the galaxy itself. And then from this proper motion, you can actually get what we call full 6-dimensional phase space. So this is just like 3D velocity. So, X, Y, and Z, or radial and tangential velocity, and which then you can also get a total velocity from. And, X, Y, Z, or 3D positional, just like distance information. And so we have this amazing, very detailed, like, kinematic or dynamic information for many of our ultrafaints and many of the satellites around the Milky Way, just because of Gaia. So I wanted to take this really precise, just wealth of information, observational information that we have, and see what it would tell us about the Milky Way's dark matter halo. So in these simulations, like Elvis and the predecessor that I used for the work that I'm currently on, called Fat Elvis, all of these have slightly different masses of their host dark matter halo to kind of get a full range of what is possible for the Milky Way system. So my idea with this project is to compare these Gaia observations to the Fat Elvis simulations to see if I can pull out which of the galaxies or which of the hosts best represents the new observational information. And that'll help us constrain the actual mass of the Milky Way's dark matter halo. So Fat Elvis is the predecessor, or the successor of Elvis. It's the next generation of Elvis. Instead of having 48 Milky Way-like and Andromeda-like hosts, there's only 24. But 12 of these are the dark matter only, so just dark matter in the simulation. And 12 kind of get at this subhalo destruction that I talked about earlier, but by still only using gravity as the physics in the simulation. So they do this by embedding a gravitational potential in the center of the dark matter halo and of the host dark matter halo. And this gravitational potential is a way to mimic all of the visible matter or the baryonic matter that actually makes up the Milky Way galaxy and us and everything that we see. But there's a lot more physics going on in the universe than just gravity. But all of those physics, if we're talking about a simulation, costs a lot of money and takes a lot of time and a lot of computing power to create, and we just don't know physics perfectly. That's why we're all here doing research. So embedding this gravitational potential is kind of a way to get at these extra effects that we do actually see without having to make larger and more expensive simulations. So 12 of the hosts have this embedded gravitational potential. And those are the ones that I focus on, because in those I don't have to go in and kind of randomly or manually destroy some of the dark matter halos so that I can get closer to the actual counts that we think there are of dark matter halos. And just to point out, this picture, this kind of 4-picture figure that I have here, on the left-hand side, the left-hand column are a dark matter only host. The top you kind of have a zoom out, and the bottom row are kind of zoomed in. And then on the left-hand side, you have the hosts that have this embedded gravitational potential, or disk potential as it's referred to. And as you can see on the kind of the outside, the dark matter only and the disk simulations look the same. They kind of seem to have the same amount of substructure or smaller dark matter halos surrounding them. And then on the bottom row, though, when you zoom in, when you're close to the center of the host dark matter halo, in the disk simulation, or the simulations with the embedded gravitational potential, there's way fewer dark matter halos in the center of that one than there is in the dark matter only simulation. And this is exactly that disruption of dark matter halos that I was talking about earlier, and that I kind of had to force into my past work. But now there's a simulation that does that for me. So this time I went in again and I grabbed subhalos that I think would house ultra-faint dwarf galaxies. But I also included some more massive galaxies that are around the Milky Way. We'd call these like classical dwarf satellites. And all of these are informed by the observations and proper motion work that Tobias Fritz et al. Did right after Gaia had its second data release. So now I can use these Gaia-derived calculations to compare to my simulations. And so I did this comparison slightly differently this time, because we know that we theorize there should be many more ultra-faint dwarf galaxies out in our Milky Way, out in the universe, than we've actually been able to observe. So there's this idea of an observational incompleteness. We're not seeing as many ultra-faints as are out there. So to kind of eliminate some of those completeness concerns, I matched my observations to simulations by distance. So for every observed galaxy in my set, so as you can see, I started out with a set of 36 satellite galaxies. I just excluded the Sagittarius dwarf galaxy because there's a lot of observational evidence that Sagittarius is actually one of the satellites, one of the galaxies who is being physically like disrupted by being so close to the Milky Way galaxy. Like it's actually being torn apart right now if you go and look at these gorgeous pictures of Sag and the Sagittarius streams. So I'm ignoring that one because it's complicated with Sag. So I have my set of 36 satellite galaxies. I have distances, and I have the full 6D, six-dimensional phase-space information for these satellites. So for every one of these, I said, okay, if I have a satellite that's at a distance of 100 kiloparsecs away, then in the simulation, I'm going to gather all of the subhalos that live within 95 to 105 kiloparsecs from its host. So there's a little 10 kiloparsec wide bin of subhalos that I collect for that one galaxy satellite that's 100 kiloparsecs away. So in this way, I'm distance matching. So just what subhalos live in what areas, and galaxies, what galaxies live in what areas, and then I'm comparing those two. And as you can see, I missed a part. So I have my little bin, I have my collection of dark matter halos that live in this specific distance bin for each galaxy. And then I randomly select 10 of those. So I have 36 observed galaxies and 360 subhalos, simulated halos, to kind of, now I have two distributions, an observed distribution and a simulated distribution to compare. And as you can see, these comparisons are very, very tight. So the one other thing that I did here is I took the 12 Elvis hosts that have the disk embedded in them, and I broke them up into 3 host mass bins. So there's 4 lighter or lower mass hosts, there's 4 intermediate hosts, and 4 massive hosts. And I did the distance matching between the observations and the simulations in each of these 3 hosts. So the magenta, cyan, and yellow lines each have 306, or each comprised of 360 subhalos, and the black line is 36 observed halos, or observed galaxies. And so again, you can see that within the gray shaded errors, these are a great match. So distance-wise, our observations are looking, or our simulations are looking almost exactly like our observations. So now I can take these distributions, these subhalos, and compare them to other parts of the dynamic information that we have from Gaia. And so I wanted to start out doing this with radial velocity, because prior to Gaia and prior to this really detailed proper motion information, there was a lot of strong, robust observations of line of sight velocity, or the radial velocity that a satellite galaxy has compared to the Milky Way. And so let's just compare our sets of subhalos to Fritz's radial velocity information and see if before Gaia was around, what was this kind of analysis telling us about the mass of the Milky Way's dark matter halo. And as you can see, just kind of comparing by eye, it's tending towards a smaller or less massive Milky Way dark matter halo. Okay, so, but now that we have Gaia, what is this more robust, this more detailed kinematic information telling us? So what are the tangential and radial velocities telling us? Well, they are actually preferring, if you look at by eye, they're actually preferring a more massive host, a much more massive host, dark matter halo. So I did some statistical comparisons. I used the Mann-Whitney U test, which just compares two distributions to see if they're pulled from the same distribution. And I got out the p-value. So this is the p-value that you've heard in statistics. If the p-value is less than 0.05, you can reject the null hypothesis. And for my work here, the null hypothesis is the observed galaxies and the simulated subhalos come from the same distribution. So if I have a very small p-value, then I can confidently say the observed galaxies and the simulated subhalos are not from the same distribution. So that simulated dark matter host is not representative of the Milky Way's actual dark matter halo. And as you can see from the p-values in these legends, they're all very, very, very small. We're getting close to something with on the left-hand side, the tangential yellow line. It's the best fit of all of these. But one thing that isn't taken into account in this kind of big set of 36 satellites is that many of these proper motions have pretty large error bars on them. Gaia is amazing, and just the more information that's going to come out of it will improve this, but it's not great right now in many aspects. So what I did was I said, okay, let me take into account the fact that a lot of these proper motions have high error bars. And so I went into my sample of 36 observed galaxies, and I excluded any galaxy whose tangential velocity error was 25% or more of its actual tangential velocity. So did it have a high tangential velocity error? And I excluded it if it did. And so that left me with 22 galaxies that had small proper motion errors. And so now I redid the comparison. I say, okay, great. So I have this sample that's a little more reliable because it has smaller error bars. What does this comparison say when I do the distance matching again? And as you can see, the p-values for the teal or for the cyan lines, which are the intermediate mass host dark matter halos, are actually fit. And so we can more confidently say that this improved 60 phase space information is suggesting that the Milky Way's dark matter halo mass is actually a little bit larger than we have canonically thought beforehand. So that work I am finishing up right now. I am writing the paper. It'll hopefully be out very, very soon. And so yeah, that's the science that I have for you today. And I wanted to end real quick on kind of my journey through STEM and through academia. So as David had mentioned, I started out Mount San Antonio College. And I'll talk about that a little bit, but at Cal State Long Beach, I was able to do Camp Hair, and I interned at the SETI Institute up in Mountain View, California. It was amazing. It was the internship I did that made me go, oh, I want to do this forever. Like this is it. I got to use the Allen Telescope Array. It's a radio telescope that you see here up at the Hat Creek Observatory, and I literally got paid for a summer to look for aliens. It was great, and I did so by using these telescopes and sifting through just huge data sets. So I got a really great introduction to kind of big data analysis as well, which was just amazing to me. I was in the very first CalBridge cohort. The picture in the upper left-hand corner are the five of us, the very first scholars. And I think myself and Arturo will be graduating hopefully next academic year. And then I've also been able to connect with a lot of other scholars, a lot of more junior scholars to me at UC Irvine. So the picture on the bottom left are all of the scholars that were at UC Irvine. And, as you all know, in the CalBridge community, Jose very, very unfortunately passed away last year. And so rest in peace, Jose, as always. I always miss him. But he was an amazing person, and he was such an amazing part of the community that, I don't know. Okay, sorry. Moving on. So just to get back to a little bit of my journey, I did start at Mount SAC. I very much did not have this kind of linear, I always wanted to do science. And so I went to a community college and then a Cal State. I actually did not start at Cal State Long Beach, where I did my undergrad, until I was in my mid-20s. So at first I wanted to be an actress, and I was in the Army Reserves because I didn't know what I wanted to do with my life, and I had to financially take care of myself. So I needed a job. And I also ended up working at Disneyland. I was friends with Pooh Bear because it kind of combined my love of wanting to be an actor and kind of all things like theatrical and just Disneyland. So I did that for a while, and it was great, and I had a lot of fun. But as I was taking just a ton of classes at Mount SAC, I realized that I wanted to really dedicate myself to something. I realized that I just didn't like acting as much as I thought I did when I went into it. I didn't like being a musician as much as I thought I did when I was, playing in the high school band and playing around with friends. So then I just kind of took a second to reflect and realize that the thing that I loved the most, that I had kind of always loved but was never encouraged to explore, was science and was physics. So I applied to go to Cal State Long Beach in the amazing physics department there. I actually started by doing condensed matter research, which was really cool. But it just didn't click for me. I loved it. I had a really great experience doing it. But like I said, when I got to do Camp Hair and go to SETI Institute, that's when I was like, oh, and it was just that kind of light bulb thing where you're like, oh, this is it. this is what I want to do. So I had an amazing experience at Cal State Long Beach. I applied my senior year for, while I was in CalBridge. This was my first year as a CalBridge scholar, was my senior year. I applied for graduate programs and I got into 0 of them. And through the mentorship and support that I received from the CalBridge scholars, my CalBridge mentors, the department, the faculty, and my peers at Cal State Long Beach, I decided to keep going, and I applied to do the master's program at Cal State Long Beach. And so I did a year of that. So in the first year, I reapplied for graduate school and reapplied for the NSF. And I got the NSF and I got into 3 graduate programs. And so I chose to go to UCI, which is where my CalBridge UC mentor was from. And I'm continuing to work with him. And now at UCI, I realized as I was putting this together, I don't really have great pictures of my time at UCI because I just take a lot of pictures while I'm working from Snapchat that I never post. But it's been a really, really amazing time at UCI. And I've been able to do a lot to give back to the communities that I've come from. And so these last few minutes, I just wanted to focus on kind of the peer mentoring work that I do. So as David mentioned, I am a board member of the Astronomical Society of the Pacific. So I do a lot of work with them on how to diversify their membership, how to get, how to do science literacy work with more and more populations of folks that are underserved, and how to get their really amazing, the ASP is really amazing, educational training tools to grad students that want to do outreach and have great connections to communities that deserve that kind of work. And that's great and it's fulfilling and I love it. But I think in light of the strike for scholars, or the scholar strike today, I really wanted to talk about peer mentoring. I think with a lot of diversity, equity, and inclusion work as grad students or undergrad students, there's not a ton we can do. There's a lot that we can do, but as a grad student, my goal is to do a lot of research and graduate and do well enough in grad school that I can become a postdoc and that I can eventually become faculty. So there's a lot taking up my plate, and I'm only in my department for a handful of years, as any student is. We're only around for, not that long. So it can seem very daunting when what really needs to happen is, the university leadership and the faculty. Those are the people that need to be doing this work. And a lot of them are starting to and are and have been, but more of them need to be. And, and then there's also that idea of we as students, we didn't create this system that is oppressing us in many ways. So it's not our job to fix it. But there's a lot that we can do. And for me, peer mentoring has been kind of my answer or my way to improve my community of peers and this growing diverse community of scientists that CalBridge is really, really fostering. So because of my experiences with just great mentoring in general through CalBridge, when I got into UCI in my second year, I saw this need by working with the Inclusive Excellence Committee. There was this need that students wanted more mentorship and they wanted peer mentorship. And so I had this idea to create a peer mentoring program. And my good friend Ariana Long and I, so we started this program where once a month for about an hour for an entire academic year, or every academic year, we have peer mentoring sessions for the first year graduate students. And we talk about things like anti-racism and imposter syndrome and a lot of topics that are talked about in CalBridge, but we do it with everybody. And we do it to really normalize all the stressors that we're going through and start to really build that community so that we as students and as peers all feel safe around each other or have some level of safety around each other and openness. And then because of that, I started doing the peer mentoring work in CalBridge. And so I do a lot of this kind of peer mentoring work, and I really, really enjoy it. And sometimes for me, I worry that like I'm doing too much of it. So if y'all heard Gabor's talk 2 weeks ago, when he said that, I think it resonated with a lot of us scholars and students when he said that you can be an amazing scientist and do DEI work. And so I just kind of wanted to highlight how I am already starting to see that that is true. And so I wanted to just, tell especially the students and the scholars that it's possible. So at UCI, because of my work with PACE and because of the research that I do, I have been awarded the Latino Excellence and Achievement Award for 2020. And in 2019, I was awarded the Tom Engel Fellowship for Mentorship. So, this is kind of reaffirming that I can do both DEI work and research. And then in CalBridge this year, I became the director of peer mentoring. So you will continue to hear from me, CalBridge scholars, about peer mentoring. But I just wanted to end on that note that while it seems like within our community as students, we don't have a ton of power. And while that is true, we do have some power, and you do have a voice, and your voice matters, and speaking your voice and your truth and all that good stuff is really important. And there are things that you can do to really impact your community and make your experience in grad school that much better. So with that, I just wanted to thank everybody again so much for coming and spending time with me. My website is there, but you'll also be able to email me and I'll be around for questions. So thank you.
Thank you so much, Katie, for that excellent talk, and thank you for sharing about your story. That was really, really great. So for the audience,
thank you.
Yeah, no, thank you. For the audience, if you have any questions for Katie, either about her science or any of these excellent programs she's been working in, you're welcome to post your questions in the Q&A chat, and then we can address them. I also want to mention for any students who are in attendance, certainly our CalBridge scholars, but even students who are not CalBridge scholars, we will be having an informal chat with Katie after this talk. And if you're interested in joining for that sort of informal chat, just shoot me a message and I'll send you the link for that. So first though, are there any questions from the audience, again, about the science or?
Well, while we're waiting for people to type up questions, I guess I can ask one about the science. Very remarkable, the being able to trace the quenching of these ultrafaint dwarfs to reionization. And I wonder if you can now turn this around and use that to study reionization. Can you use the infall times and the masses of things that are quenched and not quenched to tell you more about epoch or patchiness of reionization or anything interesting like that?
Yeah, so that actually is something I was just talking to some colleagues about, being able to, use those infall times, but more specifically, use just these Milky Way-like simulations to look at various limits to the masses of dark matter halos at reionization that would stop formation. So yeah, like how big is tiny, essentially, but back at reionization. And so that's actually something that I'm going to start looking into with another grad student at Irvine, Francisco Mercado. We're going to look at in Fat Elvis, yeah, how big do we think this reionization ended at? And that'll kind of be able to tell us a little bit more about reionization.
Very cool. Great.
Thanks. Yeah.
And I don't know if you can see, I think there's a question in the chat from Lydia about your plans after the PhD. Can you see those, Katy?
Oh, yes, I can.
Yeah, so the question is,
awesome.
What are your plans after PhD? Also, oh, and then a bit of personal information.
Yeah. So hi, Lydia. Thanks for the question. Yeah, my plans after the PhD are to, I guess the ultimate goal is to become faculty in Southern California one day. But I want to do, oh, sorry, my daughter has joined me. She's going to join us for Q&A. Yes. I want to apply for postdocs. So I'm going to definitely apply for, like, when you're applying for postdocs, for the students that don't know, you can apply for like to work with a specific faculty, but there's also a lot of postdoc fellowships that are similar to like the NSF. So I'll be applying for those as well. Yeah. And then I see another question from Amy. Roughly how much larger have you determined the dark matter halo around the Milky Way is? And is it most likely true for other galaxies' dark matter halos as well? That's a good question. How much larger? So we think the Milky Way, from that work, we think the Milky Way's dark matter halo is only slightly more massive than we would canonically think. Prior to, or I think one of the lowest limits that we think right now is that the mass of the Milky Way's dark matter halo is a little less than like 10 to the 12, and now we're thinking it's just slightly more. So it's only a small bump in the mass of the Milky Way. And then we haven't done this kind of work, or I haven't done this kind of work on other large galaxies' dark matter halos, but you certainly can do this similar work with simulation. And then another question, how can we calculate, oh, it went away.
Oh, and this calculate the age of a quenched galaxy?
Oh, okay. So we do the age of a quenched galaxy through, oh, not the coffee, baby. Sorry. We do the age of the galaxy through looking at the chemical composition of the stars. And the way that the ultrafaints, the plots that I showed, we're using a color magnitude diagram. So you kind of compare these abundances to different simulation, different models of galaxy ages, and kind of just get the closest. So it's again comparing observations to models that we think are correct. And then, hold on.
And there's a question from Wing, which is, what was one of the greatest barriers you experienced during your undergrad, master, or PhD, and how did you overcome the barrier?
Oh, that's a good question. So I think the biggest, especially in my undergrad and master's, was coming from studying theater to taking physics classes. It's a very different way to learn and to study. And I'm kind of naturally introverted and shy. So it took a lot for me to learn how to ask questions and like go to office hours and that kind of stuff. And I really started doing that when I was a master's student, and then I did it a ton as a graduate student. And that like changed everything about the way that I learn physics and understand, and actually even are able to do research. And the way that I did that was through my peers. In undergrad, I made a small group of friends that I felt comfortable with, and then a larger group of friends, and then all of those friends were physics majors, and then a lot of us started the masters together. And it took a while. It maybe wasn't the most time effective way to do it, but I just got comfortable in larger and larger settings to asking like physics questions.
And then I think this next one should be our last talk, since we're pretty much out of time. It says, you're doing a lot of good work. How do you balance science, equity, and mentorship? All of these things.
Oh, yeah. So I actually do a lot of time tracking. So from many years ago, when I went through the CalBridge time management workshop, I remembered Alex talking about like this breakdown of, how many hours you should put into studying, and as an undergrad, how much you should do studying, how much should you research, that kind of thing. And I've just kind of have kept that balance. So my goal is for my work week, however many hours that is, I try to get 80% of my work to be research, and then, 15% to be everything else. And then there's like 5% of answering emails and whatnot. And so that, I think it's still difficult, because 80% in doing 15% equity and mentorship work looks like I'm doing 3 times more work than 80% of research, because research can be so slow. So for me, it's also a little bit of just trusting in the process of knowing like I'm putting this many hours into research and I feel good about the progress that I'm making. It's slower than a lot of other work, but I think I'm still pretty happy with the balance.
Great. Thank you so much. And thank you.
Thank you.
Yeah. And
yeah.
Are there any students interested in coming to the informal chat, which we'll switch right over to the other Zoom right after this, just shoot me a message. Yeah, and thank you so much, Katy.
Awesome. Thank you. Yeah, thank you so much, Alex, and thanks to all of the other organizers and attendees. Yeah, and so I'll just hop right over to the next Zoom.
Yes, I emailed it to you.
Okay. Awesome. Thank you. Okay. See you all there.